Molecular geometry and polarity. This is a set of guided notes that I've used in the past regarding what polar bonds are and how that relates to molecular geometry when we try to figure out if a molecule is polar or not. Just want to cover some basic vocabulary before we get started with this. When we talk about molecules, that is atoms that are bound together in a structure, we have to be very clear about molecules versus bonds, right? Molecules are made up of bonded atoms. It's not the other way around. Just be very careful with the vocabulary that you're using so that you can communicate about this clearly. So here we go. Covalent bonds, we have non-metal atoms that are basically playing tug-of-war with each other over valence electrons. And not all covalent bonds are the same, right? We have cases where the electrons are being shared evenly because the electronegativities between the two atoms are relatively similar, or we have cases where the electrons are being shared unevenly because the one atom is pulling harder on the electrons than the other one. So that results in nonpolar and polar covalent bonds respectively. And what does that really mean? Nonpolar bonds, where the electrons are distributed evenly, means that, well, there are no partial charges present. The electrons are evenly distributed between the two atoms in that bond, so all the charges are kind of balanced out. In the case of a polar bond, since the electrons have sort of shifted to one side, that side of the bond becomes partially negative, since electrons are negative, and the other side of the bond becomes partially positive because the electrons have shifted away from it, right? Creating a permanent pair of partial charges, a partial negative on the side that the electrons have shifted to, the atom with the higher electronegativity, and a partial positive side on the side of the bond that the electrons have shifted away from. So we're going to explore what the implications are for polar bonds in molecules and when molecules are polar later. But for now, let's just focus on structurally understanding how to determine if a bond is polar and then how to determine if a molecule is polar. At the bottom of this page here, there are some calculations about electronegativity differences, and the thresholds for electronegativity difference in terms of bond polarity are listed above. I did the math here. The answer key is posted to Schoology as well, but the difference in electronegativity for each of these bonds falls either above 0.4 or below 0.4, and definitely below 1.7 because we are done talking about ionic bonds in this class. In this case here, the double bond between carbon and oxygen. Carbon's electronegativity is 2.55, oxygen's is 3.44. The difference between them is 0.89, which qualifies as a polar bond since it is greater than 0.4 but still less than 1.7. As a result, the electrons in this bond will shift closer towards oxygen permanently because oxygen is pulling on them harder with that stronger electronegativity. And as a result, the partial negative charge forms on oxygen and the partial positive charge would form on carbon because the electrons are shifting towards oxygen. Right. Oppositely, in this case here with carbon and hydrogen, the electronegativities between carbon and hydrogen are so similar that the difference is only 0.35. Now it's not zero, so the electrons are shifted a little bit, but in the world of chemistry we say that since the difference is less than 0.4, it's not really enough for partial charges to form. So the electrons have a little bit of leeway to move around, but they haven't shifted enough to cause permanent partial charges to form along this bond, and thus we say that this bond is non-polar. And then we have two examples of polar bonds down here. But what I really want to get to is the backside here, where we take the idea of polar bonds and the concept of molecular geometry, and we pair that together to think about whether or not a molecule is polar. Is this collection of bonded atoms polar or not? And just because a molecule has polar bonds does not guarantee that the molecule will be polar. And that's where we have to think about geometry. Here's what's up. To be considered a polar molecule, the molecule must have at least a polar bond, at least one, and be symmetrical, or be asymmetrical, excuse me. It cannot be a mirror image of itself in any dimension. If it was, then the polarity would cancel out. In order for a molecule to be nonpolar, either of these must be true. If it's symmetrical, even if it has polar bonds, it's going to be a nonpolar molecule because those polar bonds will cancel out. If it has no polar bonds in it, then it's definitely going to be nonpolar because there's nothing polar about it. But let's see how we can figure out whether or not a molecule is polar by drawing the structure and analyzing its geometry. Let's start with H2O. Okay? Start with oxygen as my central atom because it can bond to two things. Hydrogen can each only bond to one. Okay? And then I will form the bonds here. Great. There's my structure for H2O. Now I need to do the electronegativity difference calculation to make sure that I have polar bonds in this structure. The electronegativity of oxygen is 3.44, and I know that from looking at the electronegativity table, and hydrogen is 2.20. Calculating that difference, you find that the difference in electronegativity is 1.24. That is very much a polar bond. It's greater than 0.4, but it's less than 1.7. So this is a polar bond. Which way are the electrons going to shift? They're going to shift in the direction of oxygen. And we show this with an arrow that has a little bit of a tag on the tail. I always thought about this tag as being kind of like a plus sign because it shows you where the positive side of the bond is, and which way the electrons are shifting to is the negative side of the bond. And the same thing is true here. The electrons are shifting towards oxygen because it's the same bond. Now, this results in a partially negative charge on oxygen and partial positive charges on each hydrogen. But how do I know that? How do I know for sure that this molecule will have these partial charges? These bonds are each polar, but the partial charges that form are actually going to stay as part of the molecule because this molecule is asymmetrical. And a way that we can check for that is by looking to see in 3 dimensions if it's asymmetrical. First, I'll look vertically. So if I were to check with a vertical line straight down through this structure, I see that on the left side of that line, we have an unshared pair, and on the right side, we have a hydrogen atom. Already, we've proven that this is asymmetrical. And if you prove that it's asymmetrical in even 1 dimension, the whole molecule remains asymmetrical, even if it's symmetrical in the other 2 directions. So it is asymmetrical, and it has polar bonds. Therefore, H2O is a polar molecule. All right. Now, for our next example, CCl4. I'm going to do this one for you. Carbon goes in the middle with its 4 valence electrons. Great. And then we're going to put a chlorine atom on each side of carbon because chlorine can bond to 1 thing, whereas carbon can bond to 4 things. There we go. And the key detail to checking for symmetry with these Lewis structures, you have to draw the clean, finalized structure. If you have a bunch of loopy bonds and it's a messy structure, it's not going to be possible for you to check for symmetry. So you got to be careful about that. If you need refreshers on how to draw Lewis structures, please contact me and I will get you resources. Okay, so I can check for polar bonds now. We got the difference in electronegativity between carbon and chlorine. And I don't have to do that calculation 4 times either because they're all the same. So carbon's electronegativity again is, or not again, but 2.55. Chlorine, 3.16. The difference between them, I believe, is 3.61. Or excuse me, 0.61. Yeah, okay. 0.61. That is greater than 0.4 and less than 1.7. Now, before I start drawing the bond dipoles like I did over here, I kind of jumped the gun on that. I am going to check for symmetry on this molecule. If I check vertically, up and down, I see that chlorine is reflected on both sides. If I check horizontally, I see that chlorine is reflected on both sides. Now I have to check diagonally. Do we have chlorines on both sides? Yes, and down here as well. So this molecule is symmetrical in all 3 directions, vertically, horizontally, and diagonally. Therefore, it is a nonpolar molecule, despite the fact that it has polar bonds. So CCl4 is a nonpolar molecule. Okay. I'm going to do the next 2 for you as well. NH3. Okay. So if we draw nitrogen's Lewis dot diagram with its 5 valence electrons, and we have 3 hydrogens, each can bond 1 time, I'm going to bond it here, and here, and here. Okay. Calculating the electronegativity difference of NH3, ammonia. Well, let's see, N and H. Let's see, what is the electronegativity of nitrogen? 3.04, and hydrogen is 2.20. The difference in electronegativity here is going to be 0.84. Right? With that difference in electronegativity of 0.84, I have 3 bonds that are polar, and now I get to check for symmetry. Okay? Vertically speaking, it bisects this bond here, but we have hydrogens on both sides. Horizontally speaking, I have an unshared pair on top and a hydrogen on the bottom. It's not symmetrical. So it is asymmetrical with polar bonds. Therefore, NH3 is polar as a molecule. It is polar molecule. Sorry. Here we go. CO2. Last but not least, and I am going to be a little bit faster with this drawing. This is an example we've done a lot in class, and I want to be very clear about it. The double bond to this oxygen and the double bond to the other oxygen. That's our structure. It's a linear molecule. Now, right away, I don't even need to do the electronegativity difference calculation for this question, and I'll show you why. If I check vertically, it's symmetrical. If I check horizontally, well, it's a line. It's pretty symmetrical. And if I check diagonally, sure, it's symmetrical. So since it's automatically symmetrical, we don't even need to calculate the electronegativity difference unless it was specifically requested. This is a nonpolar molecule because it has symmetry. And just in case you were curious, the bonds in this molecule are polar. The difference in electronegativity between carbon and oxygen, as we saw on the last page, is 0.89, and that's a polar bond. But since the polar bonds are pulling in equal and opposite directions, they cancel each other out. The electrons won't shift because one's trying to pull them that way, the other's trying to pull them that way. They cancel each other out in terms of their polarity, so the molecule is nonpolar despite the fact that those bonds would be polar. Okay. Try the next 2 and the 4 on the last page, and if you get stuck or need help, shoot me an email. I hope you guys enjoyed the video, and let me know if you need help with anything else.